Okay, so we'd said last week about starting up, and we'd said that for many systems like a PC or a Mac, what it'll do is it will search around looking for some hardware to make sure it's got enough hardware to actually run something. Once it's then done that, in general, what it will look for is some hardware with a more substantial operating system, because you could call the Bootstrap an operating system, but it doesn't really do a lot. So it goes to look for a hard disk or an SSD or a USB or something that's got an operating system on it, and it then transfers control to that. That is the operating system that we think of. So when you start up your computer, if you look at the screen, you'll often see messages saying checking hardware before the Windows thing starts. But computers these days are so fast, it quite often just flashes through. So that's what the Bootstrap program is doing. Starting up the computer, checking the hardware, and then going and looking for another operating system. But you can extend that thought. If that's what it's doing, if it's going to look for another program to run, and remember, an operating system is a program like anything else. Somebody's written it at some point. If you're going to look for another program to run, why can't that other program be a program that doesn't run an operating system, but allows you to point to different operating systems? In other words, a simple menu system that says something like run Windows or run Linux. And there's been comments about struggling to find material relevant. So to give you a hint of where you're going with this one, Google something called Grub, G-R-U-B. And Grub is exactly that. It's a Bootstrap loader, which allows you to choose, excuse me, it allows you to choose from a set of operating systems, all of which are installed on the hard disk. Early PCs couldn't do that. Early PCs were tied to the operating system being on the first part of the hard disk, and that was built into the Bootstrap loader. More recent operating systems allow you to have the operating system anywhere on the disk. And the question is, Grub's just for Linux, right? And the answer is no, it's not. Grub will work with anything. So you can install multiple different operating systems and choose from them. Is that okay with that question? And part of the reason I wanted to talk about Grub is I'm almost certain that it was in the presentation from last week. And it's definitely in the book. So I'm hoping you've all got the book, and that will also point you to other things. Yeah, so is that okay for that question?
Yeah. Perfect, thank you.
Okay, I'm seeing some nods, so I'll move on, see what the next one is. 5 services provided by an operating system. And again, I'm not going to do this in detail because I definitely remember talking about this last week, because we talked about things like file systems and user interfaces and I/O systems. So it's those kinds of things. So go back to the notes and have a look at all of those different bits. Because remember, we were also talking about them in terms of monolithic operating systems, where all of these things are in one big chunk, as opposed to hierarchical operating systems where you can load in different bits depending on what you want to run. And we also said things like Windows takes both approaches, so it's quite a lot baked into the main operating system, but there's other things that you add in. And you know that you add them in because if you add in a printer or a Stream Deck or whatever, you add in device drivers so that the operating system can talk to that device. So go back to the materials and look at things like file system, IO system, and all that kind of stuff. Remember that diagram we had that was circles with all the different bits, starting at the kernel, working its way out to the user interface. Have a think of all the things in there. Five major activities of an operating system with regard to process management. So I'm not going to do that because we're doing that today, and I don't know why this has ended up in last week's tutorial. So apologies for that. Oh, yes, I do know why it is. So remember I said we've cut out a lot of things. So in the presentation, I didn't cover all of this. So we did talk about processes, we did talk about memory management, and that was the sort of things that operating systems do. But in some of the slides, there's more details about what memory management actually needs. So I can remember in the slides, we talked about memory management saying things like not letting one program bash into another to keep them separate, to decide where it goes in memory, that type of thing. So there are headings about that in the slides, but there's more detail about it in the book. Similarly, secondary storage management. And again, we talked about that. We talked about the idea that for Windows, you save a file. But the operating system takes care of things like, well, how do you save the name? Where specifically does it go on a device like a hard disk or an SSB? And in fact, how do you set it up so that we as users don't care whether it's going to a hard disk or a USB or whatever? And that's just three of the things that it does in terms of storage. It looks after those things for us. And I just spoke about this there when we were talking about a monolithic versus a layered operating system. So monolithic is faster because all the stuff's in one place. But whenever you want to extend it, there's a difficulty because you have to rewrite the operating system and then reinstall it. A layered approach gives you more flexibility, but because you've got different bits here and there, they have to talk to each other. And the talking to each other, just that communication, means that they're slower. So they're more flexible, but slower. Okay? I'm just sort of running through these. So if there's questions about my brief explanation, please let me know. What's the purpose of system calls? Another name for a system call is?
An interrupt?
No. Good idea, but no. Remember we talked about an API, an application program interface, in order to call the operating system, a system call, to create different things. Phaser asks, is Gentoo a monolithic operating system? No, Gentoo is a version of Unix, specifically a version of Linux. And one of the things about Linux is it is very definitely not monolithic. Linux itself refers to the kernel, so the bit that talks to the hardware. All the other bits are from all sorts of other places. So no, Gentoo is not monolithic. So a system call is that all that stuff that I did about APIs. So you call a system, you make a system call to make the mouse appear, to click on it. All of these things are controlled by the operating system. Does Gentoo require to be built each time? I'll go and look that up. My recollection was that it didn't, but I am happy to be educated. I'll go and look that up, but not right this second. I'll look it up after. what's the purpose of system programs? Well, let me give you an example of a system program. When I brought up the command line interface and I typed in dir, I was running a program. But it's a program that comes with the operating system to list the files in DOS. That's a system program. So system programs are there to help you with system things. Another one might be something called check disk, where you can check whether your hard disk is working okay. And you get the same sort of things in all sorts of operating systems. So you've got a hard disk manager. We also ran the task manager. That's a system program. It doesn't help you do work as such, but it helps you run the system and understand what's going on in the system. What's the purpose of the command interpreter? To enter programs into to enter commands into the operating system. And it's separate from the kernel because you want to be able to run different interfaces, whether that's a command line, whether it's a GUI, whether it's a different command line. And we talked about it specifically in Linux and Unix when we talked about which shells. We talked about the Unix shell and we talked about how someone rewrote it. The guy's name was Bourne. And he rewrote the shell. It was a Bourne Again shell or bash. So we can, yeah, Fraser was getting there. Greer's saying that there was an excluded section, but the practice test has a question. Apologies about that. If you get me the exact question, I will update that and take it out. I thought I'd got all of those. And the final one, what system calls have to be executed by a command interpreter or shell in order to start a new process? And again, we spoke about this specifically for Unix. And part of the reason I keep talking about Unix is, of course, your big group report is on a Unix system. And what we said for this one, for Unix, can anyone remember the command? Piece of cutlery?
Fork.
Fork. And we did talk about it in the lecture. So does that help with all of those things? We did cover them, perhaps not in great detail, but then that's part of the reason we have this. Because of course, you saw how long we took last time just covering things at a top level, and we were still running late. So this is part of what you have to do. So I'll talk about things in general, but you then have to go back and look at them in more detail. Any questions about that tutorial then, after that brief run through? And that'll maybe help in future tutorials, because hopefully they are going back to some of the stuff that were covered in the slides, and you can hopefully make that connection. Okay, if there's no other questions about that, is there questions about anything else? So that's the chapter review tutorials. So questions about anything else just now?
Is there a difference between a buffer and a cache?
That's a very good question. Okay, so what I'm trying to do is decide how detailed to be in the answer, because when we're talking about things like memory management and CPU, I'm going to go into this in more detail. So can I leave it at yes for now?
Yeah, sure.
And we will talk more about them later in the course, I promise. All right. Any other questions just now? Okay, I'm not seeing anything coming up. So what we'll do is we'll move on to chapter 3. Now remember, all of the stuff is online. We're going through it chapter by chapter. We're on to chapter 3 today, which is processes. So I'll go through it as usual. If you have questions as I'm going through it, please stop me and ask. And I'm happy to take questions as we're going through it. Okay, so we talked a wee bit about processes last week. Or we at least talked about the fact that processes exist. And you'll remember I was talking about what I think I'm running, Teams, PowerPoint, OneNote, as against what the system's running. And you remember I brought up my task manager on Windows. And as far as I'm concerned, I'm running 5 different programs. But as far as Windows is concerned, I am running hundreds of processes. So all of these things have to be run somehow. And we've only got one CPU. Now, I know that there are multiple CPU systems. I know that there are multi-core CPU systems. We will talk a wee bit about those just now, but for the moment, we are going to assume we have one computer with one CPU that can do one thing at a time, okay? And then we'll broaden it out later on about how we might make use of more CPUs and more cores. So we want to think about processes, what they are, how we are going to get all these hundreds of processes all running, and how they're going to work together. Okay, so in terms of a process you can think of as a running program. So when we talk about a program, we're talking about the thing that's sitting on your disk ready to run, but it's not running yet. Once we're running it, we call it a process. And processes have got lots of different attributes. They can also be created in different ways. And again, we touched on this last week. We talked about systems where we would run jobs, scheduled jobs that would run at a particular time. I've got a backup system running on this computer, and it doesn't run during the day because it slows down my machine. Instead, I've got it scheduled to run at 6 o'clock because I'm usually finished by then. So it backs up my computer to my network server every day at 6 o'clock. I don't have to do anything, it just runs. That's a job, it's a batch job, and it will just run on its own and I don't have to think about it. Other things will be running at the same time. So I said I've got different programs running, different user programs. Teams, PowerPoint, OneNote, whatever they happen to be. But I've only got one CPU. So I can't run these things. They're not all running at the same time. So they are timeshare, and the time that we're talking about is a CPU time. We're splitting up the time of the CPU amongst all of these processes. So it doesn't matter what we're talking about, whether we're talking about a job that's scheduled or a process that we've initiated ourselves. They're all processes, and you can think about them as being the same thing. The other thing you'll remember about a process, which is a launched program, and you'll know this from the LMC, and it's part of the reason we do the LMC, is that programs run instruction at a time. Runs an instruction, goes and gets an instruction, executes it, goes, gets the next instruction, executes that, and so on. And all our processes work in the same way. So we have the idea that the process is running sequentially, and the idea that we've got the program state. And again, if you think back to the LMC, the program state is that stuff in the middle, the program counter, where we are in the program. The registers, data that we've brought in. The accumulator, the result of a calculation. So we've got where we are in a process, and we've got the state of the process. It's the LMC, so it's a small computer. It doesn't have much in it. Larger systems have more things. Bigger CPUs have more things. But they will all have a program counter to know where they are in the program at that point. They will all have an accumulator. They might have more than one, but they will at least have an accumulator where you get the results of arithmetic calculations. But they might have other things. So they might have a stack where we have data that we're going to use again. And so it's a place we can leave data. But it tends to be short-term data. So you use a stack for short-term data. We have a data section where we store things that we're going to use all the time, global information. And we have a heap. So these are data types. And I know that some of you are doing some of that in other modules. If you're not, don't worry about it. Just remember that they exist. You have to know that because they're in blue. We said that these are likely to come up. The difference is stack is short term. So when we got our little man computer and we're entering our two numbers, they're stored in the stack. But if I'm running a word processor here, my document that I'm creating is stored in the heap. So it's for bigger data that's going to be around longer. So there's all these things going on, all as part of the process. That only happens when we execute the program. And it doesn't matter how we execute it. I don't care if it's graphically or command line. It won't happen until we do it. And in fact, executing one program might create more than one process. I am running Firefox. I don't know if you noticed, but when I ran through these processes, there was a whole set of processes all identifying themselves as Firefox. I don't have Edge running, so I don't know why there's Edge processes. One of the things that Firefox does
you're on
is
Windows.
Say that again, sorry?
Windows has Edge running, see, because you've got the search option in the search bar. That classes as Microsoft Edge.
Of course it does.
It's
I've
hidden
turned
like
off
that.
the news thing to try and save some system resources, but I do still have the search, you're quite right. So it thinks of itself as an instance of Edge, in the same way as that each tab that I have running here is a process, all controlled by the big Firefox process. So one program might be lots of processes. They have to exist somewhere. You can't run a program in CPU without it being in memory. You cannot run it from the disk. It needs to be in memory. So it has to be loaded in and be held somewhere. With all of these things that we have identified, all of these parts the code, the actual program itself, which we're going to call the text section, program counter, the stack, the heap, they all have to be stored in memory. So we have the code, the actual executable code. We have the data, and that's global data that's always going to be there. And then we have temporary data. And you'll see a couple of things here. Each process is assigned a certain amount of memory. Some of it is taken up by the text and the data, and that won't change. But some of it, so that stays the same. But some of it changes. So the stack and the heap, the temporary small bits and the temporary big bits of data will change, not surprisingly, as you're working. So in order to make best use of space, what we do is we start the stack at the top of memory. Remember we said memory go, in all these diagrams, we go from bottom of memory 0 to top of memory, which it's identifying as max. I said high last week. You get the idea though, top and bottom of memory. We start these two temporary things at opposite ends. So we start the stack at the top, and it runs down, and we start the heap at the bottom, and it goes up. The idea being we can make as much use of memory as possible. And it's only when we have so much data that these things collide in the middle that we have a problem and we run out of memory. So that's the first thing that we're doing to try and make more efficient use of the memory that we have. Okay, so far? Okay, so we've got these processes. And we talk about them being in different states. They are identified there, but the diagram here is actually more useful. So let's think about what happens when we run a process. We have a new process. And we have processes already running. So when we initiate it at this new part here, what we're really saying is we've got a new process, and if the CPU could run it, that would be lovely. Thank you. But there's lots and lots of processes. We just saw that. So instead of it running immediately, what it does is it goes into a queue saying ready. This process is ready to run if you can give it some CPU time. Remember, we're talking about sharing a CPU. It's a timeshare system. So one of the things that the operating system will do is it will run through this list of processes that are ready to run if they had CPU time. When the CPU is ready, it generates an interrupt and says, oh, I'm ready for a new process, please. At which point the next one in the list gets dispatched to the CPU and starts running. And it starts running away on the CPU. Now, there's two issues with this. One is processes that have an issue. Let me ask you a question. What do you think takes the most time for processes? What is the largest part of their execution time? Anybody want to take a guess?
Fetching the instructions.
Say it again.
Fetching the instructions.
Fetching the instructions?
From
No.
the memory.
No, it's not. Any other guesses?
Is it dealing with new processes?
Dealing with new processes? Again, good guess, but no. On your screen, you've got PowerPoint, and it says diagram of a process state. What's PowerPoint doing right now?
Idling.
Idling.
It's
Okay,
displaying.
can you? Sorry,
It's the graphical interface.
it is a graphical
But
interface, but but what's it doing right now?
Waiting
It's
for an
actually
instruction.
showing.
It's waiting. It's waiting for me to do something. And in terms of the amount of time it's spent with the CPU compared to the amount of time it's spent waiting for me to tell it what to do next, there's no comparison. And that gives us an insight into how this works. Because I've got PowerPoint running, but it's not actually doing anything. What is doing something? All those other processes that are in the background and we don't see. Or Teams, which is doing something. It's updating my screen. I can see your chat and I can see faces. So there's a couple of ways your process can stop. The first one is it's waiting. It's waiting for input, output, or an event or something. So it can, if PowerPoint is waiting for an input, there's no point in me saying, oh, give it some CPU time, because it won't do anything with it. You'll give it some CPU time and it will go, yeah, thanks very much, but nobody's told me what to do. Oh, do you want we chat while we're waiting? Absolutely no point. Get rid of it and put it into this box here, this waiting list. And what that's saying is, look, I'm waiting on something happening. Don't bother coming back to me until something's happened because I don't have anything to do. And that's something that's happened, might be me pressing a button. So PowerPoint is currently in the waiting queue. But if I press a button, it says, oh, I've had an I/O event. I will move myself back to the ready queue and I will run. And what I'm doing is running and putting up this new slide. Oh, and I'm waiting for some more input again. So I'll stop again. And if I press a button, that's what it's doing. It's going into the ready queue. It then gets some CPU time when the other processes can give it time. And then it goes back into the waiting queue to say, okay, I'm waiting for some I/O. And only once the I/O's happened does it go back into that ready queue to say, okay, can you give me some CPU time, please? So that's one of the ways that a process can pause. Anybody want to think of the other reason that the process is going to pause? Or another reason why we might want the process to pause?
Because if it's idling, then there's other processes the CPU can be working on.
That's true, but the idling is just another word for waiting. So we've covered that one. Any other reason we might want to take a process out of the running queue? To store data, like if you saved the file, well, that's true, but storing data, saving a file is input-output. So that's the same thing.
What if something more important comes up? There's like a priority issue maybe?
Oh, something more important. Yes, that might be a reason we might want to do it. If something more important turns up, we might want to interrupt the process. We might want to say, oh, something's happening. We've got some data coming in from a network. Can you please go and grab this data? Because otherwise we'll lose it. Or somebody's pressed a key. Can you go grab that key, please? Because otherwise we won't know what they've entered. So you might want to interrupt the running process to go do something else. Okay, so that's two ways that the process might stop. Any others that you might want to identify? Remembering that we've got lots of processes, all of which want some CPU time, but our CPU time is limited. Remembering also that we describe these as time-shared systems. Mohammed said crashing. That comes under the same heading as interrupt. A crash is an important thing. So yes, you have to deal with it and you might have to do something with it, but it's still an interrupt. Something unexpected is happening. The final one is this timeshare thing. We have one CPU running lots and lots of processes. So what we say is, let's give them all a certain amount of CPU time. You get some time, 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 and then you go back to the start. You get some time, you get some time, you get some time. So sometimes what we'll do is take processes out of the running box and put them into the ready queue to say, oh yeah, I still actually need CPU time, so I've not finished, I'm not waiting for IO. I could use a CPU, you've just taken me out of it. So say you're running something like, say you're rendering something on a video or an image. That'll take a lot of processing time. But while you're rendering that image, if it just takes all the CPU time, how are you going to do anything else? How are you going to run all the other stuff that's happening? So instead we use this timeshare idea. We give it some CPU time and then we go back to the other processes to get something done. Some of you will have seen times where that doesn't happen as well as we would hope it would, where the process is grabbing the CPU and you've tried to change to another running program and it doesn't quite work immediately. It takes a wee bit of time. You've probably heard me shouting at my computer for exactly that reason, because it's not running fast enough. What's happening is that in the background, it's running a different process and it hasn't given it up, because it's got to get to a point where it can stop. It can't stop halfway through an instruction because we wouldn't know what it was doing. So it's got to finish an instruction or sometimes a block of instructions. So that's how it could stop. It could stop because we're waiting for IO, or it could stop because we've given it enough time. Or it could stop because, as Mohammed said, it might crash. But that would make it terminate. So that's when we would exit and say, okay, we're terminating. Now, it could be because it's crashing, or it could be just because we've stopped the program. In either case, we've got some cleaning up to do. It was using memory, so we want to get rid of the memory that it was using and make that available to something else. It was probably showing something on the screen, so we need to take that off. We need to free up any IO that it was using. Give back the printer, give back the pen, whatever it happens to be. So that process state diagram is really important to everything that we're doing, because that's what processes do. They come in, they're created as a new process. It goes into the ready queue. When the CPU has time, it starts running, and then it will pause running, either because it's waiting for IO or because it's lost the CPU. If it's because it's waiting for some IO, it goes into the waiting queue. Once the IO has happened, it can go back into the ready queue. And if it's paused because it's run out of CPU time, it goes straight back into the ready queue, ready for the next time it gets some CPU time. Until at some point, as you saw in the Little Man computer, it stops and we run the halt program and it can terminate, freeing up all the resources that it's been using. Resources like memory. Is that okay? Because that's really fundamental to everything that we're doing from now on. You're all okay with that? Yeah, I'm getting some thumbs up, some nods. That's good. Okay. All right, so we've got all these processes all doing things, so we probably want to know something about them. So unless it's a little man computer where there's only one process running, because we run one program and then we load the next one, so it's only got one thing going. Most of our systems run lots at once, so we need some information about them. That's held in something called the process control block. A process control block. It's just a block of memory, sometimes called the task control block, but it's just got information on that task. Which part of this diagram is it's in? Is it in ready? Is it in waiting? Is it whatever? What's the program counter? Where actually are you in the list of instructions? You get registers like the accumulator. So what's the current state of those registers? Which memory does it have? Which files does it have? Or anything else, any other information that you might need to store with it. And that's really important. That process control block is really important when we do the switching. So let me give you an example of switching. So here we've got two processes, P0 on the left and P1 on the right. And I imagine the 0 and the 1 are quite small on your screen, which is why I'm pointing that out. So 0 on the left, 1 on the right. Now think back to the little man computer. Think what you've got there. You've got a program counter saying which instruction you're at. You've got the accumulator, you've got registers, you've got all that stuff in the CPU. So that's all stored in the process control block. Your process is running. It runs out of time with the CPU because you've only given it a certain amount of time. So it has to go back to the ready queue. What do we need to do to make that work? Well, what we need to do is process 0 is executing. It learns it's run out of time. So we need to store all that information. The program counter, the accumulator, the registers, everything that it needs, it stores that into process control block. Then we switch to the next process. In this case, process 1. So in this case, we've saved it. Now we need to load up process control block 1. And then we can start executing process 1. That executes for a certain amount of time, whatever time we've given processes to run. Then it stops. We then save the state of process 1 and reload process 0 despite, and then start executing again over here. So are there any issues with doing that you can see just from that diagram?
A lot of time wasted just saving and reloading.
Right, so we'll get bits where it's executing here, here, and here. But we've also got a lot of times where it's idle. This time where we are changing the process control blocks is just idle time. The CPU is still running, but it's running doing something that doesn't actually advance what we want to do. So there is overhead attached to this. And I'll say this 1,000 times during this course, it's about getting a balance. Of course, there's going to be overlap. Of course, there's going to be idle states if we have to swap processes. But what's the other side of that coin? Only running one process at once? Would you like it if you're only running one program and then you had to stop that program and run something else? So it allows us to do more than one thing in our heads. It's not really, but it allows us to pretend that we're doing more than one thing at once, which is good for us. The other thing, of course, is processes already spend a lot of time being idle. PowerPoint's idle right now, it's doing nothing. Just sitting there waiting for me to press a key. So we can make use of that, the idea that, well, actually, processes for a lot of the time don't do anything anyway. What that all works out to is we can get a system where we can run multiple processes seemingly all at once. Of course, it falls down sometimes. And again, you'll all have experienced that. You try to run too many things at once and your computer just slows down until all you see in the task manager is a big red line where it says system interrupts, because it's spending more time swapping between one process and another than it is actually doing any work. And I can always tell when my system's got to that point because it just feels as if it's stopping. Of course it's not, it's still doing lots of work, but none of it is for me. It's all to support the operating system. So again, it's about getting that balance. We're okay with that before we move on? Yep, all happy? Okay. Okay, so we've said that we have a process and it runs through its instructions and we have a program counter. What if we could have a process that could run more than one thing at once? And if you've got a system that's got more than one processor or more than one core, that would be really helpful. And I talked earlier about rendering. What if instead of rendering 1 pixel, we could render 2 or 4 at a time, depending on how many CPUs or cores that we had? To do that, we introduced something called threads. So instead of a single thread of execution, we can have multiple threads of execution. So a process can be doing lots of things at once. Either lots of instances of the same thing, or instances of different things. So if you're running if you've got a router, a network router, which is actually just a spectacularly dedicated computer, it's still got a CPU, it's still got programming language, it's still got an interface. You might run threads where one of the threads is input and one of the threads is output, because remember what a router is it takes packets of data, figures out where they're going to go and sends it out to the right place. So you could run a couple of threads, one continually taking the output, one sending the output to where it needs to go to. That's so important, we're going to have a whole chapter dedicated to that, or a whole week dedicated to that, but that will be next week. Now again, we've got some code coming up. Don't panic about the code. You're not going to be tested on code. You don't have to understand the code. I'm bringing it up to try and relate it to a real life system. In this case, specifically a Linux system. We said that we have a process control block. Well, somewhere in our system, we need to store all that. And that's how something, oh, for goodness sake, what am I doing here? Hurrah. This is how Linux does it. It has a process ID. It has a state, ready, running, waiting. It has how much time it gets. It has the time slice. How many microseconds of CPU time am I going to get? And that bit is important because of what someone said earlier, because you said you might want to have prioritization, which is true. You might decide that one process is twice as important as another and give that twice as much time. So there's nothing in the rules that says time slices all have to be equal. You can prioritize some processes over others and give them more time if that's what you want to do. So you have a whole pile of these things. Some of them will point to other things, parents and children. So I've got Firefox as the parent, and each tab is a child. And the parent points to the child, and the child points back to the parent. Okay, so we've got all this stuff and we need to decide how it's going to work together. So I think the very first question today was about timers. So there's a timer running in the background. All CPUs have a timer. It just runs. And anytime the CPU is on, it just runs all the time. And you might decide that you're going to give a process 10 clock cycles, because every one of these is a clock cycle. So the process gets 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, next. Swap process. Next process comes in. It gets 5 time cycles. 1, 2, 3, 4, 5. Switch process. Go to the next process. And so on and so on. And I very glibly said, next process. Well, which is the next process? We need some way to decide. And that's what the process scheduler does. All of those processes in your ready queue, which one comes next? And again, we're going to be talking about how we decide that. And again, it's about different competing priorities. That's not this week, that'll be later on. So we've got a scheduler that's going to decide what's coming next, and it also looks after all the different queues, all the processes that are ready, all the devices that are waiting for input that would clear something out of the wait queue. No problem, Mohammed. And as you saw before, the processes move around all these different queues based on how you write your process scheduler. And I said that for a reason. Remember, an operating system is just a program someone has written. And people have made choices about how they write that. They've decided how the scheduler should work. Is it going to give everybody the same amount of time? Are you going to build in priorities? It's up to whoever writes the operating system to decide how they're going to do that. So it starts taking note of all these things. It starts taking note of all the things in the ready queue with all their process control blocks. It starts taking note of all the devices, disks, terminal units, a display, mag tape. It really does depend. And you can see here that different processes are waiting in different things. Process 7 and process 2 are in the ready queue and they could run if they had the CPU. Processes 3, 14 and 6 are waiting for disk access. They're waiting for data coming in off the disk. Process 5 is waiting for the terminal. It's waiting for me to type a key. So all these different processes will be in different places waiting for different things, including I/O, and again, there'll be priorities for those as well. So we have this idea that we have different queues doing different things at different times. Thank you. It's okay, I don't think you're on camera. You're all safe. Key delivery. Cheers. So we have got processes coming in to the ready queue. They then get some CPU time, and then certain things could happen. If they've got I/O requests, data off the disk, key, whatever, it goes into the I/O queue until that I/O starts, and then once the I/O is finished, it goes back into the ready queue. Their time that they get could have finished. That's enough from you, stop. And it can go straight back into the ready queue. The other thing that could happen is you could fork a child, which sounds fairly vicious, but all it means is start another process, another child process. And it's the equivalent of saying take a new tab. It will start another process for that new tab. But that new process also has to wait its turn. So it doesn't immediately start just because you've told it to. It's another process that has to go back into the ready queue. So the parent and the child will be in the ready queue as well. Or you could be waiting for an interrupt. Divide by 0, so it crashes. An interrupt for the input, an interrupt for whatever. Just to make it even more complicated, there are often multiple schedulers. So you've got a short-term scheduler. What we're going to do next? What's the next process that we are going to send to the CPU? Now, you don't always have multiple schedulers. It will depend on the system. It will depend on the load. It will depend what type of operating system you have written for what kind of work. But the short-term scheduler is talking about short time increments, milliseconds, so thousands of seconds. You'll also have a long-term scheduler. And my Windows machine has that. And I know that it has that because my backup routine that runs at 6 o'clock tonight is in the long-term scheduler. So that process is there ready to run. And the long-term scheduler will run every few seconds or every few minutes saying, are there any jobs that you've said should run at a certain point? And if there are, stick them into the ready queue. You also try and balance different types of processes if you have that choice. So you might not have the choice. You might be just running whatever the user wants to run. But certain processes have certain biases. PowerPoint here has got an I/O bias. We call it I/O bound. It's spending more time waiting for me than it is actually calculating anything. Other things are what we call CPU bound. It spends more time calculating things than it does waiting. So again, video rendering or image rendering, that kind of thing, it's spending more time working out the stuff than it is waiting on me. If you can get a mix of those, that's a really good scheduler. If you can get things that are spending a lot of time in the CPU and things that are spending a lot of time in I/O, then you're making the best use of the system. So that's what we mean by a good process mix. We can get CPU bound and I/O bound all running at the same time. And some operating systems keep note of certain processes and try and figure out whether they are CPU or I/O bound and use that as part of the scheduling. So we've got short-term schedulers, long-term schedulers. Other operating systems put in what they call a medium-term scheduler. Windows is one of those things. Sometimes it can say, okay, you've got all these things running in theory, but they're not doing anything. So earlier on, I ran the copyright video, and it's running in a films and TV process on Windows. But I haven't used it for the last hour. Windows would be quite within its rights to say, look, you know, you've started this, you've said you need it, you've taken up memory space that could be used by something else. Nah, let's take it out of memory and put it somewhere like the hard disk, where it's not taking up any resources, because you're not using this, and you know you're not using this, you're not fooling anybody. So it gets taken out of memory, sticks it onto hard disk until such times as it's ready to be used. And that's called swapping. It swaps in and out of the cache, Alan, on hard disk. If you have too many processes running, if the scheduler has to do a lot of that swapping, you will see the system slow down because it's spending more time copying things to and from your long-term storage than it is actually running the program. Make sense? Other systems do it in a different way. Mobile systems, for example, don't need to think about it so much. So I can see PowerPoint, I can see Teams, I can see OneNote. If you've got a phone, you don't need to see multiple processes. So it works at it a different way. It says, okay, you've got one thing running because that's the thing that's front and center, the thing that you're looking at. But you might have multiple things in the background, like you're running, you've got Twitter running on your phone, but actually it'd be quite nice if you had a background process running that, you know, took a call, took a text. So they're in memory, they're running, but they're not displaying until such point as the operating system decides, oh, actually, you do need to display. You have a call. Okay, so we've got this idea, we've got multiple processes, we've got this idea that they change to be running on the CPU. The fancy name for that is context switching. So that bit where we saved the PCB to run the new process, this thing here, this bit in the middle is called it. I'm pointing at it on the screen that I can see rather than the screen that you can see, which doesn't really help anybody. This bit in the middle is called context switching. We're switching from process 0 to process 1. That rain's getting worse. Somebody keep an eye on the trains for me to see if they're cancelled. So this is called context switching, and as we pointed out earlier, it does take time. And the more complex it is, the more time it takes. Clearly, there's more information needs stored for Teams than there is for a phone dial. So the more information, the more complex the system, the longer it will take to switch. Some CPUs try and mitigate that. So we've said that some of the things that are saved in the PCB are the accumulator or the registers. Well, what if you provided more than one accumulator or multiple sets of registers? You could actually store them on the CPU rather than saving them somewhere. So you could say this set's for process 0, this set's for process 1, this set's for process 2, this set for process 3. And that would speed up the context switching. But that's hardware dependent. So it will depend on the CPU and how it runs. Right, we're all okay with that? Okay, so what does the operating system have to do? It has to allow you to create a process, start up a process, take some memory, give it a process ID, bring something in to run it as a program, and try to understand where it fits within the hierarchy of processes. So you might end up with something like a process tree. You start the system, that's process 0. The system starts Teams, process 1. But Teams also starts a meeting window, and that meeting window starts a poll window. Or you start, oh God, I'm doing it again. I'm pointing at the wrong screen. So you start Teams, this Teams starts a meeting window, the meeting window starts a poll window. I know that's not what it says on this screen, I'm just giving you the other examples. Or you start Chrome, and Chrome starts 2 tabs. So you start having all these processes running all connected. So the operating system has to allow you to create those. As we've said before, if you have a parent, it's going to fork. You then execute the child process until it exits. That then goes back to the parent and it can continue on. And again, don't panic. Don't need to know the code. But here's how you might do that in code. This is C. So it says process ID is fork. In other words, fork what you're doing and give me another process. If the ID is less than 0, we had a problem. If the ID is 0, it's a child process. Otherwise, wait for the parent to complete. In other words, all of these things are built into the API of the operating system. There has to be something in there for them to run. That's a similar thing for Windows. And again, if you don't understand programming, that's fine, just take my word for it. If it has to create processes, it has to get rid of them as well. So you have to have process termination. Now, termination can be tricky, depending where you are in the tree. If you're terminating this process, that's okay. Get rid of the process ID, get rid of the memory, and it's gone. But if you get rid of this process, it has to get rid of these first. Otherwise, they're just hanging about with nothing to control them. So if you delete something higher up in the tree, you also need to get rid of the ones further down. If you don't, you can start to have issues. And again, I'm sure some of you will have seen that where you have memory issues. You get to the point you've no memory left simply because there's been poor control of process creation and deletion, because you can get rid of it just by restarting your system. So just like it is in your little man computer where you run the halt command, you can exit a process. You can also terminate a child process. Now, I'll tell you now that some of the language that's used in these is changing and evolving, because some people are very upset that Linux uses the abort to get rid of a child process. Other systems use kill, and people get upset about that too. But I'm sure you get the idea. What we're saying is we don't need this anymore. Let's lose it. And for a lot of systems, you can't have the child continuing if the parent's gone. So you have to have this thing called a cascading termination. Get rid of all the stuff underneath. You also have the option of the parent getting rid of one of the children because it wants to. So you might close a tab in Chrome. And you don't want to do anything else in the parent until that tab has closed. So you say, okay, terminate child, and then wait. What you're waiting on? You're waiting on that child stopping so you can come back to the main process. Sometimes that gets confused. And as I said, you've all seen that. You've all seen systems where you've used up all your memory and it won't do anything. If there's no parent, then you get zombie processes that are just out there and there's nothing in them. And if the parent's terminated, but the child's still running about, it's an orphan. So it's still there, but it's got nothing to be attached to. And as I've said, lots of systems run like this, lots of programs run like this, including Chrome. Chrome runs one start process. That's the Chrome program. But it runs multiple sub-processes. It runs processes for each tab. It runs processes for the user interface. It runs processes for the renderer, how it actually creates the display on the screen, because you get different things depending on what's in the web page. It runs processes for each of the plugins. So if you get loads of plugins, that can take lots and lots of system memory, and getting rid of plugins can speed up the system. Okay, we're happy with that. Okay. So we've got all these things running, all these different processes all in the system, and sometimes they'll need to talk, whether they are a parent and child that need to talk to say what's been happening, or whether they are separate processes that need to communicate. So you might have the Word process and the printer process, and you need to send data from Word to printer. So there's different ways of communicating. That extends out to the idea of communicating where you have physically different computers. Like I am doing here. We're all on different computers. I am sending data to the server, the Teams server, and it's sending data out to you. And we need some way of identifying that data, and we call that a socket. And some of you will be familiar with this kind of stuff. The idea that you have an IP address where you can send data from one machine to another. Using the IP address as a unique address to send the data to, so that you know that it's going to where you wanted it to get to. Having said that, there are multiple services running on computers. So you might have your browser running. That's fine. But you also might have your email running. How do you know if the data that's coming in is supposed to be displayed on your browser or sent to your email system? Or is some video to see me making silly motions with my hand? Well, you have ports. So you can think of it like the IP address being the address of a block of flats. If you're sending a letter to that block of flats, you also give a port number, an apartment number, a door number. So it gets to the block of flats, and then it gets further subdivided to know which door it goes through. A port works in the same way for the computer. The IP address gets it to the computer, and then the port number says, this is web traffic, this is email traffic, this is game traffic, or whatever. And you'll find that different systems use different port numbers, and quite often, if you're running something that uses a new port number, it won't work. And you'll have to go to your router to say, no, I did actually mean to send data to port 5555 because that's the port my game uses. Because if you're doing security stuff, you don't want to leave open ports, because that can be a way of breaking into other systems. So again, back to that block of flats, if you know that there's nobody in flat number 3, you can break into flat number 3 and then go through the wall to get into flat 2. So you close down, you lock down all the other ports, and you only open up the ones that you need. So you can connect using sockets, using the IP address, and using these port numbers. And some port numbers are well known. So port 80, for example, is web traffic. Port 127 is for email. Some things aren't just straight data transfer. Sometimes you want to actually run a program somewhere else. So say, do any of us ever go into travel agents anymore? Say you're on a website trying to organize travel, and you need a flight, you need a hotel, you need a car hire while you're there. What you might do is send a request to a remote system to say, I need to go to this place at this time for this long. Can you please run a program in your system to tell me if you have a flight that conforms to those parameters I've sent you, or whether you have a hotel room that conforms to that. So you can send a request for another system to run a program, and then the output for that will come back to you. Again, it uses ports, so you know which one you run. So you might have systems running different programs for different outputs, excuse me. And you'll decide which one of those you want. You can have a problem because what happens if you're a Mac sending a request to a Windows server? You might speak different languages, you might work in different ways, so you might need some stuff in the middle. And there's an example there, the Microsoft Interface Definition Language, which they called that so that they could also say middle, because it works in the middle of the systems to make sure that people can talk to each other. Sometimes that can be even more tricky. You're all familiar with binary, where you have the 1s, the 2s, the 4s, the 8s, the 16s. And most of the time, that's the way you'll have been taught. But does it have to be that way? Couldn't that just as well be the 1s, 2s, 4s, 8s, 16s? Does it actually matter as long as everyone agrees? And the answer is no, it doesn't matter. But not everyone does agree. That thing there that you're looking at is how the CPU itself stores data, and it has the rather wonderful terms big endian and little endian, depending on whether the end is the big side or the little side. So if you're sending data that's big endian to another system that uses little endian, you need to swap the stuff about so it knows what you're talking about, and it knows that you're sending a 16 rather than a 1. So you get matchmaker services in the middle just to make sure that all that works. You might have other ways of communicating. You might have something called a pipe. So we're back to processes on the same system sending data to each other. And the example I used was Word and the print server. You can set up a pipe between Word and the print server to send data from one process to the other. That's unidirectional. And unidirectional won't work for that, because one of the other things you want to know is whether or not you've printed it. So the printer can send back data saying, oh, we're done, or no paper, or toner out. So that's a bidirectional pipe, so you can send data both ways. And everybody send data at once? Can you send data both ways at once, or does everybody have to wait? You only send one set of wires, so send a message, send another message. In other words, is it full or half duplex? Is there an implied relationship? Is one master of the other? So do you have a parent-child relationship? So you can set up all these things within a system to send data, depending on what it is you want to do with that system. And where you have multiple pipes, where you're sending multiple things, you can even name them. So you can name the communications devices that are going between those processes. And Unix and Windows systems all have those named pipes in order to allow you to do that. And that is that. Does anybody have any questions? I'm not seeing any hands. I'm not seeing any. I'm not seeing anything in the chat. And sadly, I am not seeing that my trains have been cancelled, so it looks like I can come to Paisley after all.
Seen on the trains it says they're all on alert and they're all got speed limits as well.
Oh, are they?
So, yeah. But that, to be fair, that's from where I'm travelling. We're going to Glasgow Central to Paisley.
Yeah, no problem, Frank. I understand. And in fact, if I'm late, you'll know it's for exactly the same reason. Oh, yes, Teams. Thank you, Kelly. I completely forgot. So, for Teams in Lanarkshire, yes, if you can self-organise. If you can't, remind Henry that he needs to finish off creating the teams. And I've just reminded myself that I need to finish off creating the teams in Paisley as well. So if there's anybody who wants to rejoin or join another team, let me know. Otherwise, I'll do what I said last week and just assign them randomly. Any other questions? Okay, let me stop the recording.